Predicting the exact distance of a rugby kick is a complex challenge. It relies on a combination of different physical variables working together. When you have a long list of potential predictors, like different strength and flexibility metrics, it is difficult to know which ones actually impact the outcome. To solve this, we will use multiple linear regression in JASP to filter out useless variables and generate a concrete, usable predictive equation. Before we start, make sure you have JASP open, the rugby kick CSV file loaded, and a basic understanding of simple linear regression. Mastering this technique condenses overwhelming, messy datasets into a single, focused mathematical tool for real-world prediction. Let's set up the model. Navigate to the top menu and select Linear Regression. Assign your target outcome, distance, into the dependent variable box. Place all 5 of the leg strength and flexibility variables into the covariates box. Leave the entry method set to Enter. Now, navigate down to the Statistics dropdown to prepare our diagnostic safety checks. You need exact checkboxes here. Tick Estimates, Model Fit, Collinearity Diagnostics, and Durbin-Watson. Also, ensure Case-Wise Diagnostics is checked and set greater than 3. Without checking these specific diagnostic boxes, we have no way to verify if the mathematical model JASP generates is actually trustworthy. Review the output from the default Enter method. The ANOVA table shows a significant p-value of 0.017, suggesting the model works. But look down at the coefficients table. Despite the model passing, absolutely none of the individual predictors are significant. Every p-value is above 0.05. This occurs because of multi-collinearity. When predictor variables are too highly correlated with each other, they obscure each other's individual impact on the model. We can identify this in the variance inflation factor, or VIF column. Notice the high average, which sits around 5. The thresholds here are rigid. An average VIF above 1, or any single VIF above 10, indicates the model is biased by overlapping variables. The default Enter method failed because it blindly forced redundant data together. We need a smarter method to filter these variables. Return to the main settings pane to change our entry method and fix the collinearity issue. Change the method from Enter to Backward. This commands JASP to calculate multiple models, systematically stripping out the weakest predictors step by step. Scroll to the newly generated data and look straight at Model 4 to see the final result. The result is clear. Right and bilateral strength are the only surviving variables. Their p-values are significant, and VIF is down to a healthy 1.5. Before we use this model, we must verify the underlying statistical assumptions of homoscedasticity and normality. Open your Plots dropdown and tick Residuals versus Predicted and the QQ plot. This scatter plot shows your residuals versus predicted values. The random cloud of dots around the 0 line provides evidence that homoscedasticity hasn't been violated. And this QQ plot with dots tightly hugging the diagonal line suggests our residuals follow a normal distribution. Passing these final visual checks indicates our refined 2-variable model is statistically sound and ready to be turned into a usable tool. Now for the final step, translating these abstract JASP tables into a tangible, real-world mathematical formula. Guide your eyes back to the correct column in the Model 4 table. You must use the unstandardized column, not the standard error. The blueprint for a multiple regression equation is y equals the constant plus the first variable's coefficient plus the second variable's coefficient. Plugging the unstandardized numbers into that blueprint, distance equals our constant of 46.251 plus 3.914 times right strength plus 2.009 times bilateral strength. You can now take any athlete's strength metrics, plug them into this exact formula, and accurately predict their kicking distance.